I want to just start by saying if you were expecting a long timescale talk, I'm not going to do that. I've focused a lot in most of the last 20 years actually on relatively short timescales because I'm interested in what's happening now in Antarctica especially. But the main takeaway I want you to get from this talk is the ice core constraints really matter because our instrumental records are actually just too short and sparse. And I think we've learned a lot from them. And I think there's a lot more that could be done. I want to just start with a few acknowledgements. I'm going back a full 20 plus years in terms of the research that I've done and or been involved in. And I just want to acknowledge a bunch of key people. Dave Schneider, who was my first student, first grad student. Gemma O'Connor, who is my most recent grad student who graduated last year, now in UW Oceanography. And I've worked quite a bit with folks at BASS and more recently Yoshi Nakayama, who's here, of course, and Chinghua Ding, who was a postdoc with me for a few years, and we've done a lot of work together too, and I've learned a huge amount from all of these people. I do have one long time scale thing. We now know, in my view, for certain that the Western Arctic ice sheet collapsed during the last interglacial. Every proposal I've ever written, even ones about Greenland, I've said, we need to know if the Western Arctic ice sheet collapsed during the last interglacial. I'm going to have to come up with a new first sentence. If you haven't read this paper, I really encourage you to read it. It's very cool. I spent about 3 hours talking with the first author. Suddenly her first name is escaping me, Sally Lau, I think. She's very convincing. And I think it's kind of fun. I think it's kind of fun that it's a biologist that solved a problem glaciologists have used to justify their existence for, at least I have, for a long time. Okay, so Helen showed this at the first talk yesterday, I think it was. We all know Antarctic ice shelves are melting, and we know that the reason they're melting, especially in the Western Arctic and especially in the Amundsen Sea, is because that's where the circumpolar deep water is, and evidently where it's changing the most. But we have pretty short records of this. We have very sparse records. And even for the atmosphere, which certainly must be involved in driving this change, our records are very short and sparse. And this is really the subject of a lot of my work, is trying to understand what has the atmosphere done and how is it linked to the ocean and therefore the ice sheet change. So as in many talks about Antarctic ice sheet change, there's been a lot of focus on Pine Island Glacier and Thwaites Glacier and associated glaciers in the Amundsen Sea and Baymet area. Obviously, there are other important changes too. I'm not going to talk about those. I don't understand them. And there's also much less data. So again, this is something I'm sure everybody knows, but just to reiterate, there's a lot of complex processes involved. The thermal forcing of the ice shelves, the heating from below, from circumpolar deep water, is certainly a major important driver. If you make a simple calculation about the current rates of melt and retreat that are occurring, it has to have changed sometime in the last century, or it would be much further retreated already. And so something must have changed to cause this, and it's not just global warming. That's too simple an answer. Something about the inflow of circumpolar deep water has changed, and ultimately that has to be driven by something in the atmosphere. Even though the details of the processes certainly have to do with things like sea ice, which I've also been trying to avoid for 20 years, and I've discovered I can't because it's really important. So the climatological picture of the Southern Ocean, right? You have wind stress, the circumpolar westerlies surrounding the ocean, and this leads to a tilting of the isopycnals. This is sort of the mean state. This is the mean state from this great review paper by Marshall and Spear from 10 years ago or so. Contours are density. This is temperature. This is salinity. Because we know the circumpolar westerlies have been increasing, there's a general and sort of commonly assumed view that this explains why the ice sheet is melting, because circumpolar deep water is upwelling because of that wind stress. So if it's changing, there must be more upwelling, and that must explain everything. And this is oversimplified at best. I think it's probably an overstatement to say this is wrong, but I think it's clear that it's not actually the important thing happening now from the point of view of these glaciers in particular. So I want to review just a little bit why emphasis on the circumpolar westerlies, besides that general sort of cartoonish view, but also there's been quite a lot of work suggesting from both modeling and observational evidence that if you zoom into the to the Pine Island thwaites, here are those ice shelves, here's the Amundsen Sea embayment, and this is the bathymetry. If you zoom into this area and you look at the winds along the continental shelf break here, I think the next picture shows this. Here's the same picture, but now with the temperature maximum everywhere. So circumpolar deep water offshore, and as Yoshi showed in his simulations, the infiltration of circumpolar deep water onto the shelf and down the troughs towards the glaciers. The sort of very simplified wind field is westerlies north of the shelf break, coastal easterlies driven by the katabatic winds and the Coriolis effect. And that gives you the wind stress curl, which should cause upwelling and does cause upwelling of circumpolar deep water. And going back to 2008, a really seminal paper by Malta-Toma showed that in at the time, relatively high resolution ocean model, if you force the ocean model with observed winds changes, you get more circumpolar deep water flow as those westerlies increase because the wind stress curl changes appropriately. And furthermore, I think the next plot will show this. Actually, I want to emphasize something related to this, which is that there's no question that transport of circumpolar deep water onto the shelf is the process of concern here. This is not about circumpolar deep water itself warming. That is certainly happening, but I think this simulation from Caitlin Naughton at Bass, which is a future simulation, really illustrates this nicely. In these simulations with this high-resolution ocean model, she finds a temperature trend of circumpolar deep water overall of 1/4 degree per century, but on the shelf it's more than 1.5 degrees per century. This is a model, so we know it happened. The winds changed because they were imposed to change, and you got more circumpolar deep water onto the shelf. The relationship, I was really glad to see the first two talks in this context. The connections between the tropics and the Southern Ocean are strong, probably in both directions. I'm always kind of amazed when I look at this plot from a paper by Paul Holland, that's actually 2019. If you look at the winds in this little box in green here, just the zonal wind direction, the zonal wind speed in that little box, here's the Amundsen Sea embayment. The interannual variability is essentially 100% El Nino. It's just kind of amazing. So this is the wind in the zonal direction in the Pine Islands Thwaites Trough region. I've never liked that term, but anyway, compared with, so the blue is the wind, the black is the wind stress, the Southern Oscillation Index, negative in red, the IPO index, the interdecadal and interannual variability of the winds in that area are dominated by ENSO, and that's important. If you look at the sort of climatological picture, at least from the observations that we have of a transect going along the shelf from the deep ocean towards Pine Island Glacier, this is from Pierre Dutreuil's work. There's the circumpolar deep water, there's the thermocline that Yoshi talked about. We know that that varies up and down, and we know that it varies up and down with ENSO, at least for the observations that we have. Here's 2009. That was an El Nino year. It wasn't a very strong El Nino year, but it was the strongest year in which there are as good observations as we have, as are available. The shelf break westerly winds were weakly westerly, as they typically are, and the thermocline was high. That is, there was a lot of circumpolar deep water getting onto the shelf. So that's consistent with that sort of simple conceptual model about the shelf break. Conceptual and numerical models show that this affects the inflow, that the westerly strength at the shelf break matters. And 2012 followed a very strong La Nina. It was actually an incredible year. 2011, for 6 months, the winds at the shelf break were easterly with almost no fluctuations in the westerly direction. And in complete, beautiful agreement with that earlier work, you saw a measurable decline in the thermocline depth and a 50% melt rate decrease at that time. And it's worth noting that, a really great paper by Fernando Paulo, who worked with Helen, also showed that you can see this in the snowfall and the thickness of the ice shelves through time from satellite remote sensing. So all of this is to say variability on ENSO timescales matter, and it really seems to be it is connected with westerly winds at the edge of the continental shelf. And modeling evidence from the past and empirical data like this kind of make this all hang together, and it seems like we understand everything. However, well, I won't get to the however quite yet. So let's take a look at some ice core data. This is just a beautiful shot from a very old section of ice. It's about 50,000 years ago. I'm not going back that far in time. Early in my career, I was involved in a project to drill ice cores all over Antarctica. This is a pretty old plot. There are many more, of course, now, but we drilled cores in particular in West Antarctica, and I think it's, again, kind of amazing to think about. There's one weather station in West Antarctica that's been there for a long time. Imagine having one weather station in, say, Denver and going, oh yeah, we understand climate variability in the United States. That's the equivalent scale that we're talking about. So there's actually a lot more data from ice cores than there is from weather stations. And of course, they go back much further in time. Some of them, like Waste Divide, go back 68,000 years. Some of these go back a couple thousand. Almost all of them go back a couple hundred years. And to put this in perspective, here's that one weather station. I haven't updated this recently. It obviously goes to 2025 now. And in fact, there's been a bit of cooling. But the overall picture from the Bird weather station, which was put in 1957, is kind of a warming trend. And if this is all you knew, you might think, oh, global warming, things are warming up. It's also worth noting that the ERA 5 time period that's reliable at these latitudes is 79 onwards. Before that, it's useless. Please don't use it. That's really, really short. You can't say anything about trends on the timescales that are relevant here, looking at those data. You need weather stations and you need ice cores. So here's just part of the ice core record going back to 1800. And it quickly becomes obvious that this trend is not a significant change relative to the decadal variability, right? What I'm showing here is the oxygen 18 anomaly for all the ice cores we drilled, averaged together across all of West Antarctica, and including part of the Antarctic Peninsula. And then in the gray shading is the 10-year running mean standard error, to just give you a sense of the variability. I should note that there are differences between the western and the eastern sectors of the Western Arctic ice sheet, which this kind of, you don't see some of those important patterns here, and I could talk about that in a separate talk. It's probably important, but for now, just to get a sense of what the decadal variability looks like. On one other kind of neat thing, every single high peak here, if you're above 1.5 standard deviations, is a recorded El Nino event, except one, which is 1980, which is right there, I think, which is the lowest sea ice extent in that sector in the entire record. So, oh yeah, one more thing to say about this. So 018, what is this? I'm going to claim later that this tells us something about winds, and you will all go, what is he doing? This is a proxy for temperature, but the thing is, it's a climate variable. It reflects the history of evaporation and atmospheric motion and precipitation, and the way you get higher 018 values on the Western Arctic ice sheet and warmer temperatures is because of atmospheric circulation changes. So I would actually argue, and statistically this is true, it's a better proxy for atmospheric circulation changes than those other variables. Okay, one other little note about this. There is actually a trend. It's not statistically significant, but it's, that if you draw a trend line, you get a slight trend in the data. I mentioned that all these events are El Nino events. There was a really big, long-lived El Nino event in the 1940s. It's actually the most significant El Nino event in terms of impact on global temperature in the entire 20th century. It's often kind of ignored, and in fact, it's not even in all compilations of El Ninos because there was a very Central Pacific El Nino record, and some traditional measures of El Nino miss it. The reason this is important is that I speculated in 2012 in a paper with Tsinghua that El Nino event must have created a strong westerly anomaly along the coast. And it was such a big event, I said, this probably mattered. Maybe the ice sheet noticed. There's now 2 papers, and I heard someone mention 3 now, that have looked at sediment cores from beneath the ice shelf and have concluded for Pine Island and Thwaites that the ice shelf was grounded on this ridge until about 1940 and then retreated. I don't know if these are actually connected, but I really like the timing of those relationships. Okay, so all of that background on the long-term climate variability, the importance of ENSO, derived from the ice core analysis and other things, of course, led to a collaboration with Paul Holland in a paper that we published in Nature Geosciences in 2019. And I want to walk you through a bit what we did here. So Paul's insight was, well, ice core data are nice, but it's 018, Eric. We can't use this for anything. But what we can do is, from the insights gained from that analysis, recognizing the importance of ENSO variability. Let's take a look in particular at the tropical pacemaker simulations that had been done by Dave Schneider, my former student, and Claire Desser just a couple years earlier. And Paul argues in the paper that we don't know exactly what happened in the last 100 years, but this is the best estimate we have. A climate simulation, an ensemble of climate simulations, which is tied to the tropics and what actually happened in the tropics, because this is likely to give us our best estimate of the long-term variations and the short-scale variations. So this is the ensemble mean of the 20 pacemaker members at the time. This is CSM1, and then all the different members. And you can see they're all actually quite similar in their decadal variability. Again, what's plotted here is the winds in that little box at the shelf break. There's this slight trend, and there's this large variability, which agrees very well with the observed winds and is not constrained to be in agreement with the observed winds, except that it's constrained by the tropics, which determine those winds, as we saw from the statistics. In comparison, here are the free-running simulations. So this is the large ensemble. That also has a trend, but it's actually weaker than the trend that's constrained by the tropics. One of the reasons I went along with this whole crazy idea was that it captures my favorite event, the 1940s El Nino. And, it's kind of qualitatively similar to the ice core record. And I thought, yeah, okay, that's a reasonable estimate of what happened. So if you take that time series and you actually look, oh, wait, one more important plot here. It turns out that if you look at all of these different CMIP5 at the time models, and you look at the pattern and magnitude of the winds in the Amundsen Sea area, it happens that CSM1 was the best. It has the least bias. And Paul showed that if you look at the magnitude of the bias versus the magnitude of the trend in the winds of the shelf break, these CSM1 lens and pace simulations have the least bias and the strongest trend. So that gave us even more confidence. This is really what happened in this area at this time. And so there was significant westerly trends at the continental shelf break over the last century. So we're like, this is the solution. It is about large-scale circumpolar westerlies. And what we specifically said is that so this is the zonal wind over that full time period, 1920 to 2005. And what we found in these pacemaker simulations is that in that little box next to the Amundsen Sea, the winds are westerly, and it's clearly connected visually with a large-scale westerly. So end of story. Richard Alley called to congratulate me for having solved the problem. We concluded in the Holland et al. 2019 paper that the shelf break westerly trend is part of the large-scale circumpolar trend, and is the forcing that matters. This is why the ice sheet's melting. It's all great, but it's wrong. So, well, I guess that's all I need to say. You can go away. No. So I had a student, Gemma O'Connor, who had started with me, I think in 2019. And knowing that Paul was right, and knowing that I had ice core data that I could do more with, and simultaneously I'd begun working with Greg Haycomb in atmospheric sciences on data assimilation applied to paleoclimate proxies, I basically said, Gemma, let's do this. I know what the answer is going to be. Paul's right. We'll publish a great paper saying not only models but data show you the same thing. So I won't go into this at all, but it's just a cartoon illustration of what we're doing. It's borrowing from data assimilation methods used for weather forecasting, but it's applying it to paleoclimate data. So you take the data, you use the model as your prior to look at the covariance patterns. You run it through and you go around and you get new revised estimates of the climate state. And you can do this for any variable. You can get bad results because you'll always get some relationship, but you can do it carefully as Gemma did. And she did this over and over and over again. And we tried so hard to show that Paul was right. And what we found is that when you use the same climate model, but you constrain it to agree with ice core data and other global data, that sure, there's circumpolar westerly trends that's hard to get away from, but down in the Pine Island, Thwaites, Amundsen Sea area, this is not extending down that far. That's what our results showed. And we concluded that something else is happening. So the trend here is actually neutral or easterly, not the same direction that we had said in Paul's paper that it was. This shows results, Gemma's results for 4 different climate model priors. This is the lens and pace model, so the same models that Paul was using, but now constrained. A couple of others are here. We have a different pattern. We still have the circumpolar westerlies, but again, you can see there's blue along the continental shelf break there. And if you look at the sea level pressure here, the pattern is very different than just zonal average. This is the Amundsen Sea low, and it's strengthening, and you see it in all of the different results. This just shows, again, the same thing, but now we're tracking the Amundsen Sea low using a standard index of the Amundsen Sea low. So over the last century, it's deepening, and it seems like there's kind of a step change around the 1940s or 50s. So if you were to only look at ERA5 data starting at 79, you wouldn't know anything about this. There actually is a slight trend, but our results suggest there's a longer-term trend. Simultaneously to Gemma's work, Quentin de Leyden and the Belgian group with Hugh Goss did the same thing using the same data, more or less, but a different data assimilation scheme. We were very mad because his paper was published a couple months earlier, but then we realized this is really good. Someone else has validated our results, or at least reproduced our results. He actually did a longer reconstruction, but again, you can see this, again, the Amundsen Sea low index. It's varying, but it's basically higher than the second half of the 20th century throughout the last couple hundred years. So the conclusion from that work is the Amundsen Sea low has changed and is trending, okay? And this is very different from the perspective of the Amundsen Sea than the large-scale westerlies. I'm just reminding again that ERA 5 time period is too short. Okay, so in our results, of course, you still see the large-scale circumpolar westerlies change. And actually, these things tend to go together in our results and in Quentin's results. They're correlated with one another. Here's the SAM index, here's the ASL index. Amundsen Sea low is deepening, westerlies are getting stronger. It turns out that some earlier work, back to 2009, for example, argued that strengthening Amundsen Sea low is actually a part of the ozone and CO2 forced changes. This is an asymmetrical response to the symmetrical forcing, if you will. In that paper, John Turner pointed out that not all models do this. So it was kind of a weak result, but it was at least suggestive. And it's worth just noting, here's the circumpolar winds, and here's the Amundsen sea low. They're going the same direction, but locally that's an easterly along the continental shelf break. And here's Gemma's reconstruction zoomed in this area. I know I'm running out of time. What does that say? Okay, good. That's perfect, actually. So Compton wrote a couple of papers in which he tried to look at this, or didn't try, he did look at this, and he concluded from a bunch of careful simulations and formal detection attribution studies that in fact the Amundsen sea low deepening is anthropogenically forced trend, which is kind of nice. I have to say I'm a little bit skeptical. It's just two models. They actually give quite different results. One has high sensitivity to ozone and one has almost no sensitivity to ozone. So not to criticize the paper at all, just that I think there's a lot more work to be done. Just to explain what we're looking at here, this is the sea level pressure in the Amundsen sea low area. He's tracking it around. That's the reconstruction in black, and then, the reconstruction looks like that, but this is using all forcings and then isolating greenhouse gas and ozone forcings. And so when you add the greenhouse gases and ozone, you get the trend. Okay, so a summary about the atmospheric points. Shelf break wind trends are not westerly in this area. The coastal wind, near coastal wind trends that we see are actually associated with the Amundsen sea low strengthening, not large-scale westerlies, i.e. the SAM, but both the SAM and the Amundsen sea low may be a forced response. They're related to one another. A caveat, going back to the previous talks, the Amundsen sea low is strongly influenced by the tropics, and tropical freestone, I think, autocorrect. Tropical response to greenhouse gases actually, isn't that funny? It's different in different models, and there are feedbacks in both directions. And what actually happens in the model in the Amundsen Sea probably does depend on what happens in the same model in the tropics. So there's a lot more research to be done here. I'm glad that I'm out of time because partly I don't want to talk about the next section because it's confusing. But I do want to just give a couple of points from Gemma's paper in Press in Nature Geosciences. So I started by talking about what's changing the Antarctic ice sheet. And I'm now saying it's not the zonal westerlies. Well, so what is it? If the zonal westerlies don't explain circumpolar deep water advection onto the continental shelf, what does? Well, it turns out that if you actually look at this carefully, the pattern of the Amundsen sea low is not mostly an easterly trend along the continental shelf break. It's actually a northerly trend. So zoomed into that area, here's the ensemble mean of her reconstruction, and here's the northerly winds, so stronger southward winds through time. What Gemma found is that, and this is where Yoshi comes in, she worked with Yoshi to do a bunch of idealized simulations using MIT GCM at high resolution, driven by winds designed to ask this question, basically, what's happening if it's not the circumpolar westerly, or not the shelf break westerlies? And it turns out that you get more circumpolar deep water flow onto the continental shelf when you have northerly winds, and you get less when you have southerly winds. And this turns out to be a complex function of the wind effect on the sea ice and the buoyancy forcing and the response of that density changes, density differences between the inner shelf and the outer shelf on the circulation. And sea ice and polynya turn out to play a huge role in this, which means I have to start thinking about wind-driven polynya changes, and I don't want to do that. So Ruth Mormon is going to solve this for us. And I have a few more slides, but I'll just cut to the end and answer questions about this. Just to summarize, we should stop talking about the SAM and the westerlies. It's not what is driving it, although it is part of the large-scale dynamics for sure that's relevant. If there's a simple story, it's really about the Amundsen sea low. But it's really then about local processes on the continental shelf having to do with buoyancy change, sea ice, et cetera. There's a lot more work to do here. The current state of the art does suggest this is tied to anthropogenic forcing, but I think we have a lot of work to do before that's just a known fact that we all believe to be true. And I will stop there. Yoshi.
If there's no question, great talk, thanks a lot. So your first point, we should all stop talking about salmon estuaries. Do you think this statement applies to East Antarctic as well, or specific to West Antarctic?
Well, as you showed, Totten Glacier is very different because the bathymetry is very different, and I don't know. I think what I would say is, okay, maybe don't stop talking about it all, but don't just assume that because it's this large thing that it explains the regional changes that are happening. The Antarctic ice sheet collapse problem is fundamentally a regional climate problem, and we just have to get away from sort of zonal average pictures.
So one more follow-up question.
Yeah.
The reconstruction that JAMA created, do you think we can trust them for East Antarctic, or the ice core data is heavily concentrated in West Antarctic?
Yeah, thanks for pointing that out. So unfortunately, the snowfall in East Antarctica is too low in most places, and we simply don't have the same quality or density of ice core records from there to do this sort of thing. So if you look at Gemma's first paper on this, the verification statistics outside the Pacific sector are not very good. So more work has to be done to do something about that. And I'm not sure how to do it, actually, because there simply aren't enough good places to go to get the kind of data that we used in West Antarctica.
Thank you.
Alex?
Nice talk, Eric.
Thanks.
So the longer reconstruction that you showed, going back to 1800, showed that you had some warming, right, over the 19th century. And I'm wondering, given that, let's say for Pine Island, right, the onset of the change, I mean, it was associated with an El Nino event in 1940, but presumably because El Nino events are always happening, there had been preconditioning that may have occurred before then in terms of what the climate was doing to the ice shelf and the glacier to get it to that point where a big El Nino event could unpin it. Is it possible that what we're seeing is really just the delayed response to what happened in the 19th century?
That's an interesting question. So, I mean, I've struggled with a lot of aspects of this. That 1940s El Nino event is a massive event. It's not as obvious here. If you look at reconstructions of sea surface temperature in the tropics, or in fact, if you look at Greenland temperature history, 1940 stands out. It's a global scale event. But there's a lot of events in the 19th century, decadal variability trends, as you said, very large El Nino events. It has always seemed really implausible to me that the ice sheet, that the ocean circulation around Antarctica didn't care enough about any of these until some point. So my main thought about that is that event can't be the event. But it perhaps, as you alluded to, was sort of the final straw on maybe long-term trends. And there is sort of supporting evidence for this in the sediment core data from Smith and others, and suddenly Hillebrand and others, 2019, I think, 2017. The sediment core beneath the Pine Island ice shelf and seaward of it shows changes in C13, the proxy for circumpolar deep water, shifting abruptly around the 1940s. So they basically argue there's a regime shift that has occurred in the oceanographic conditions, that perhaps that is the trigger for that occurring. Okay. I don't know if I've answered your question.
Yeah, well, I was thinking you showed Quentin's the reconstruction back to 1800, and maybe I was just eyeballing it too much, but it did seem like there was a centennial trend, right, so over the 19th century.
You're talking about this. Sorry, next one. That one from content. Okay, keep in mind that's not the temperature, that's the Amundsen-Seelow index there. But actually, these things are highly correlated with one another. So I think if we look at the temperature, we're probably seeing something similar.
Maybe I'm eyeballing it too much. But,
Yeah, keep in mind, this is atmospheric temperature. It's not the ocean thermal forcing that affects the ice sheet. So yeah, I would be careful about doing that.
Great, thanks.
All right, thanks for a nice talk, Eric.
Thank you.
I have one comment and one question.
Yeah.
So on your conclusion slide, I would urge you not to throw out the role of the Westerlies. I think the way the community has gotten stuck thinking about this has been this focus on what happens at the shelf break, assuming there is this pipe from the shelf break to the ice shelf cavity to the ice shelf melt. And there's been this assumption that the supply of heat onto the shelf automatically controls what happens in the melt. And I think what we understand, and what's shown nicely in Gemma's paper, right, is that you have to understand the supply and how that is consumed. And it can get consumed because it melts the base of the ice shelf, or it can get mixed to the surface, which I haven't read Gemma's paper closely, but presumably has to do with convection, polynyas, et cetera. And so you have to put those together. And so on lots of different timescales, those will interact with each other. And then there's also exchange between the different basins. So I think putting those pieces together is really important.
Yeah, let me actually quickly respond to that and say thank you for saying that.
Yeah.
I think I get annoyed at the oversimplified statements I see. It's all about the circumpolar westerlies, and I'm going too far the other direction. It is worth remembering that, or recognizing that everything I've said is basically looking at, once you're at the shelf break, what happens? But of course, other papers, including some by Yoshi, for example, have said, well, actually, this is about the supply. There's some interesting relationships between, for example, the Ross gyre and the way it delivers heat to that area, which is perhaps associated with Amundsen sea low changes as well. So for sure, there's a whole other set of processes. And of course, at the larger scale, that involves the circumpolar westerlies as well. So I agree.
So we had a nice talk by Henri Drake earlier, where he was really making this argument that the way to think about this is through a closed water mass transformation or volume budgets, right? Which you have to do the formation term and the supply term plus the transformation. The question I wanted to ask, so you showed that it's the meridional winds that impact the variability. It's a nice paper by Julia Hazel from 2019 that comes to a similar result.
Yes.
So my question is it the vertical mixing due to changes in the sea ice, or is the wind stress curl, because you have a very strong wind stress curl over the shelf, just heaving the density surfaces up and down?
So part of me wants to ask you to turn to Yoshi and ask him this. But what I will just say is that in our paper, what we conclude is happening in our simulations is that as the meridional winds are persistent, because we did idealized simulations, so we're just letting them be persistent. What you find is that the polynya close, which changes the heat budget, which changes and the freshwater budget, which affects the meridional density gradient, which actually changes the strength of the undercurrent at the shelf break, which changes how much circumpolar deep water gets on. There are undoubtedly other processes happening in our simulations, not to mention the real world that also may be important and or perhaps more important.
Okay, great. Thanks so much.
Yeah, thank you.
Hey, thanks for the great talk. I was curious how much you've thought about ice shelf basal melt feedbacks. In particular, there's this wonderful paper in 2024 by Yidong Fangse that's about it kind of poses that the undercurrent is a product of basal melt itself. And I was wondering how that fits into this.
Yeah, so I didn't add the slide from the paper on this, but what we actually find, again, in our idealized simulations is that you start at a sort of neutral state and you start increasing the winds and you just let them go. That changes the sea ice, which changes the density structure, which changes the advection of heat, which melts the ice sheet, because we don't have an interactive ice sheet, but it is melting in response to the forcing. After a couple of years, the freshwater anomalies resulting from that ice sheet melting become larger than the freshwater anomalies resulting from the sea ice changes, and then actually dominate. So in our simulations, we could probably turn off the winds and it would continue to persist. So I don't think there's any contradiction there. I think it's actually really consistent. Yeah, thanks.
Thanks, Eric. Cool talk. I have two questions. The first is easy. Could you go to the slide that you skipped over that shows Gemma's sort of buoyancy plinia mechanism?
Right.
The paper
Where is
press. So I've talked to her about this, and I just want a
right
refresher of how this
that
works
it?
because it's complex.
Yeah. Is that what you're referring to? Yeah.
Yeah. I'd love if you could walk us through this. And then my second question related is, do you think there's any other locations around Antarctica where this mechanism might be active? Maybe a naive question.
I am going to not answer the second question because I just, all of my work has focused on this area. Again, there's so much more data, and the simulations we've looked at focus on this area. Actually, in Gemma's simulations, we also include a Bellingshausen Sea. That's part of the domain, and actually the same process occurs there. So I guess I did answer it. Sure, it probably matters elsewhere. So here's the cartoon view. Normal conditions, westerly winds at the continental shelf break, open polynya, so you're losing heat, undercurrent, eastward undercurrent along the continental shelf, heat transport. As you start closing the polynyas because of the wind field that's been applied, you decrease the surface heat loss, and you also stop forming sea ice, right? So that's like a negative freshwater forcing, positive freshwater forcing. So the inner shelf starts to freshen, and now you have increased density gradient between the outer and the inner shelf. In our simulations, but also well established in literature, is that rather like the jet stream being driven by pressure gradients between low and high latitudes, the strength of the undercurrent is driven by the strength of that, the gradient in density. So the undercurrent starts to speed up, and eddies coming off of that undercurrent are known to be the actual mechanism by which circumpolar deep water gets under the shelf. Thought, I should say. And then, as that happens, you start getting more and more ice melt, and that is just a self-reinforcing mechanism.
Thanks. Yeah, I'll offer the suggestion to Gemma, but I think this is really, we really need to look at instrumented seal observations and see if you can see this mechanism happening in the real world.
Yeah, I totally agree. I wish there were more observations. I also think there's sufficient that somebody could do a PhD project to figure this out. But it is that scale of project to get all the data together and look at it. Yeah. Yeah.
Hi. So as you probably know, physical models are getting close to being able to represent those interactions between polynyas, ice shelf, landfast ice, icebergs, under ice shelf, currents, etc. So I was wondering, under the hypothesis that such models will be available in the next couple of months or years, what kind of idealized experiment would you realize to test the hypothesis that buoyancy fluxes or maybe other processes are actually contributing to sucking that CDW? So can you imagine a protocol that would be useful? Yeah,
I'd love to sit down and write some notes down with you to talk about that, but I personally would love to repeat essentially the same experiments that Gemma did with a model that has the interactive ice sheet. I should note just quickly, what she did was she took observed winds from specific years and just repeated them so that we had a longer term, so we could get rid of the noise, basically. Like ask, what if it's persistent for 5 years? And the argument for doing that was that we really want a century scale change. And it turns out that in Caitlin Naughton's excellent work from the British Antarctic Survey, even though the papers that they wrote initially talked about westerly winds as the driver, the results are actually the same. In those simulations over the century scale, the difference between cool and warm runs is dominated by whether you have northerly or southerly winds. But yeah, let's sit down and talk about that. That would be great.
Chingwa, can I, one more comment? Because I just want to follow up on Ethan's comment. If you're interested, Ruth has looked at this observationally a little bit, and so there's a poster up there. And so the suggestion here is that there should be a correlation between the stratification and the thickness of that CDW layer. And as you said, there's not a lot of observations, but you can go to a few ice shelves in West Antarctica, say in front of Dotson, and you see this scenario here that when you get these thick CDW layers, you get this capping at the top of it, which gives you this feedback. And so it's in the observations as well.
Yeah, great, thank you. I did talk to Ruth yesterday, and I saw her poster, and I immediately ran back to my computer to make sure we'd cited her, which we did. Thanks.
Very interesting work. My question is maybe less scientific, but the simplest explanation is often not just one that is scientifically appealing, especially when there's not as much evidence, but is also easier to sort of communicate to friends and family and general public. But when that starts to break down, like what do you say when someone says like, why is the ice in Antarctica melting? Like how do you give a explanation?
Man, I'm going to try to answer this question pretending that November 2024 didn't happen. I mean, what I say to people is it's not air temperature, it's ocean temperature that matters. It's not that it's getting warmer, it's that the amount of warm water that's getting to the ice is changing because of the winds. And I stop right there. And I think that's okay when you're talking about public communication. If somebody's more of an expert, you can say, well, it's regional winds that are complex. But the honest answer is, I think, I'm telling a story here about winds because ultimately the winds are driving the ocean. But it is possible that all of this is wrong and that it's really about precipitation changes, for example, which also have buoyancy changes. I don't think that's likely. We've looked at that a little bit, but I think the reality is it's an open question, and I think we can be honest about that. I don't think the anthropogenic link to ice sheet melts is yet demonstrated. And I think we should be honest about that, even though it seems awfully likely that it's true.
Thank you. Thank you so much. Thank you very much. And let's move on to our final invited talk by the